This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 4 of our series, Mastering Lab Techniques Safely. In today's episode titled Separating Mixtures with Techniques, we're going to explore the fascinating world of how to effectively separate different components in a mixture. Whether you're a budding scientist or just curious about the process, today you'll learn some essential techniques that make this task both safe and efficient. So, let's dive in. In most factories, more money is spent quietly separating stuff than on the dramatic chemical reactions. A cloudy beaker on your bench, steam racing up a glass column, a funnel balancing a swirl of liquids, all hiding one puzzle. What's the single smartest way to pull them apart? A single mixture can hide many different stories at once: solids suspended in liquids, dissolved salts, volatile solvents, stubborn traces of water. The trick is noticing which story matters most for your goal. Do you care about recovering a solvent, isolating a pure crystal, or removing a contaminant down to parts per million? Each priority points you toward a different technique, and a different order in which to use it. A pharmaceutical plant drying an active ingredient, a brewery polishing its product, and a clean room keeping air particle-free all rely on the same menu of tools, but they combine them in distinct ways. In this episode, you'll move from simply getting things apart to deliberately designing separation steps, choosing when filtration beats centrifugation, when distillation outperforms extraction, and when a short packed column can save you hours. A surprising amount of separation strategy is actually about what you don't do. Distilling a heat-sensitive component just because the apparatus is free, or shaking two immiscible liquids without checking densities, can quietly destroy yield. Industrial processes are tuned to tiny physical quirks: an azeotrope that refuses to budge, particles that slip through the wrong pore size, droplets that cling to glass instead of settling. In the lab, you face the same physics on a smaller scale. Your real power lies in spotting which property, size, phase, volatility, solubility, density, or surface affinity, gives you the biggest leverage first. Start by asking a blunt question. What single physical property gives you the cheapest, cleanest win first? Size, phase, volatility, solubility, density, or surface affinity are all candidates, but they're rarely equal. A practical way to think is in layers of difficulty. Level 1. Coarse, low-energy moves. If a solid has already formed or phases are already separate, exploit that before you touch heat or exotic solvents. Gravity, gentle pressure, and existing phase boundaries are almost free. Level 2. Modest energy or equipment. Heating to moderate temperatures, simple packed columns, or a straightforward liquid step to move one component into a friendlier phase. This is where a 10-centimeter packed column can quietly turn an all-day reflux into a manageable run by giving you more theoretical plates per unit height. Level 3. Precision and constraint-driven tricks. When azeotropes, tight safety limits, or extreme purities appear, you start layering strategies. Pressure swing distillation to sidestep the ethanol, water azeotrope, or carefully staged extractions to chase down ppm-level impurities. Now flip the perspective. Instead of asking, how do I separate X from Y? Ask, which properties are useless here? If both components have nearly identical boiling points, volatility is a dead end. Reach for solubility or surface affinity instead. If everything is fully dissolved and non-volatile, heating just wastes energy. You might need an extraction or a crystallization path. Real processes rarely stop at one step. A biotech plant might clarify a broth, polish it through a membrane, concentrate by distillation, then finish with drying. Each step hands a cleaner, simpler mixture to the next, like a relay race through different physical properties. Your best guide is often what fails. Droplets that won't coalesce, crystals that oil out, distillates that stubbornly plateau below target purity. Those are clues that the property you're betting on isn't giving enough contrast, and that it's time to change the story you're exploiting, not just tweak the same method harder. A semiconductor line offers a sharp example. Incoming air is a messy mix of dust sizes, but instead of filtering harder, engineers choose pore sizes and flow speeds so a HEPA unit captures 99.97% of those stubborn 0.3 micrometer particles. They're not chasing all differences, just the one that matters for defects. In a distillery, the strategy shifts. Once sugars become ethanol, the key contrast is volatility. Simple distillation boosts concentration until an unexpected plateau, the 95.6% ethanol-water azeotrope. At that point, more plates and more heat stop helping. They pivot to a new property, pressure, or a third component, to bend the vapor-liquid balance and slip past the limit. Even in a small lab, the same mindset pays off. A packed column on a stubborn purification isn't just fancy glassware, it's a compact way to stack 20 theoretical plates in 10 centimeters, turning an overnight reflux into a controlled, high-resolution climb through boiling points. Separations are quietly entering a redesign phase. Membranes that once fouled easily are gaining smarter coatings, letting them sift hot, salty streams where classic distillation struggles. Supercritical CO2 and tailor-made ionic liquids are beginning to slip into workflows as tunable shape selectors, guided by AI that adjusts flows and pressures in real time, more like an orchestra conductor than a thermostat, trading brute force heating for fine-grained control and lower footprints. In the next lab session, treat each messy sample like a small landscape: hills of solid, lakes of liquid, patches of vapor. Ask which feature is cheapest to exploit first, then sketch a two-step route, maybe a quick sieve move followed by a selective heat or solvent move. Your challenge this week? Redesign one routine cleanup using that map-first mindset. This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!